In this final set of videos, we will be studying the limit of a series. Now many of you may ask, haven't we been studying limits already? Well, I am now telling you that there is a difference between a limit of a sequence and a limit of a series, and I will use the following example to illustrate this to you. This is a pictorial example, so I hope this will help you in your visualization. Okay, let's consider a 1 meter by 1 meter square. And let's create a series of shapes as follows. Now then, let's create the shapes this way. Let us first halve this square. Okay, so my U1 is the area of the big square, which is 1 meter by 1 meter. Okay, so it's 1 square is equals to 1. Now U2 is the area of this purple shaded rectangle. Now can you tell me what this is? It's going to be half times 1, right? So it's half times 1 is going to be equals to half. Now let's create U3 by taking half of the remaining area. So then, the area of U3 is going to be equals to half times half. And this is going to be a quarter. Next, let us now take half of the remaining area. Okay, so the area of this is going to be U4, which is going to be half times 1/4, which is going to be 1/8. Now, what is the limit of the sequence of UR? Limit of the sequence of UR as R tends to infinity. What is this going to be? Can you see that as my R tends to infinity and I subsequently divide, the area is getting smaller and smaller? Yes? So are you able to visualize that eventually, as my R tends to infinity, my area is going to tend to actually a value of 0. Okay, so the limit of the sequence is actually 0. Now, what about the limit of the sum of these terms? Well, if I add up all of these shapes, all of these shaded areas, and as my n tends to infinity, obviously all the shaded areas are going to fill in the square, right? And in addition, because of U1, I have to add in the area of the square one more time. So the limit of the sum of UN as n tends to infinity, this limit is going to be equals to 2. Okay? So this is the difference between the limit of a series and the limit of a sequence. In this case, the sequence refers to the individual terms, which is the area of the individual shapes. Okay, each shaded area as follows. However, when what we are talking about is the limit of the sum, then I have to take this area and I have to add this area and add this area, 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 and eventually I'm going to cover my whole square. And because of U1, I also have to add 1, so I'm going to get a limit of 2. So I hope this example has clarified the difference between the limit of a series and the limit of a sequence. So let's enter the lecture notes and identify for ourselves how exactly we can determine the limit of a series. Now, one situation in which we have learned about the limit of a sum is actually in the chapter on APGP. If you recall, in GP, we discussed issues such as infinite sum, right? And we said that the sum to infinity, it exists only when my common ratio follows a certain condition. And in this case, we say that the geometric series is convergent and its sum to infinity is its limit. Okay, which means that the sum actually follows, it tends to a certain value, which is something like what is happening in the square over here. Now, then some of you might now ask, so in what circumstances will the limit of my sum not exist? I will leave you to think of one more example, okay, following these lines, so a geometric example, and if you can think about it, we can discuss it during the tutorial. But for now, let's move on with the lecture. So what about other series besides geometric series? How do we know whether a sum exists? So let's consider this series. Okay, for example, 1 over 1 times 2 plus 1 over 2 times 3 plus 1 over 3 times 4 plus 1 over 4 times 5. Now before you can start working with this, what you need to do is to identify the nth term. And I see that definitely the numerator must be 1, right? Based on the common pattern. And now if this is r equals to 1, then this is r times r plus 1, right? If this is r equals to 2, it is also r times r plus 1. So my nth term should be n times m plus 1. Okay? So what I have to do before I can find the sum of the limit of a series, what I must do before I can find the limit of a series is actually to find the sum of the first n terms. And this is going to be in terms of n. Okay? So if you recall, this is actually an example from the previous part, then we can handle it by using method of difference and partial fractions. So I find that my sum to n terms is always going to be in this form when I express it in terms of n. Now what happens if my n tends to infinity, so that I end up summing an infinite number of terms? You recall from the previous section, how do I take a limit of something like this? As n tends to infinity, then 1 over n plus 1 must tend to 0. So this means that Sn must tend to 1. Okay, because it's going to tend to 1 minus 0. And the way I present it in my answer is actually as follows. I'm going to write that the sum is going to be the limit as n tends to infinity of Sn, which is, when I replace my form of Sn inside, I'm going to get limit as n tends to infinity of 1 minus 1 over n plus 1. And this is equal to 1. So in this case, we say that the series above is convergent with a sum to infinity of 1, or we can also say that the limit of this series is 1. So let me quickly bring you through a definition. So if the sum to n terms is given in this form, and the limit of the sum to n terms exists, then we say that this series is convergent, which is exactly what I explained above. So sum to infinity is basically the limit as n tends to infinity of the sum to n terms. So let me write that down, because some of you might be quite daunted by all the mathematical symbols. Okay, so this basically means that sum to infinity is the limit as n tends to infinity of the sum to n terms. What are the implications on us then? This means that in order to find the sum to infinity, what I need to do is, first, I find the sum to n terms in terms of n. And then I let n tend to infinity in the expression in part 1. Okay, and whatever I get there will be my limit. So, to clarify everything once and for all, let us look at one final example before we close this series of lectures. Now, given that the series is convergent, we are going to find its limit. So once again, like what I said earlier, what we have to do is basically find Sn in terms of n and apply the limits. Okay, so if I were to write down, because over here what I'm given is not in sigma notation, so it's pretty hard for me to identify. So what I have to do is first try and write this down in terms of sigma notation. So what I see is, this is for r equals to 1, right? So this is going to be r plus 2 times r plus 3. Now for r equals to 2, do you see that the same pattern follows? Hence, the nth term is going to be 1 over r plus 2 times r plus 3. So the sum to n terms is basically going to be given of this form. Now recall that when I have something like this, okay, with two denominators that are quite close, it always helps to do partial fractions. Okay, and when I see a negative sign with two similar terms, by now all of you should be familiar, we are going to be using method of difference. Hence, my sum to n terms is of this form. So as n tends to infinity, now I'm sure many of you can confidently say this part is going to tend to 0, right? So my limit, I expect it to be 1/3. So the way we present it is actually as follows, or some people may also write as n tends to infinity, 1 over n plus 3 tends to 0, hence the sum to infinity is equals to the limit as n tends to infinity of Sn, which is equals to limit as n tends to infinity, and I substitute in the expression of Sn, which is equals to 1/3. Okay, so this concludes our entire series of lectures on summation of series. I hope that it has been a fruitful journey for all of you, and we will clarify any remaining concepts in the tutorial.